presentations caught my attention at the Berkley Agentic Summit 2026. Today was day one. I want to talk about Jim Fan and Sergey Levine. The Jim Fan presentation is about an approach towards robotics that mimics the Tesla FSD approach and incorporates large pre-training from video combined with fine-tuning of actual robotics tasks. Sergey's approach is a little bit more general, and what I find interesting about his presentation is the embodied chain of thought, or the reasoning, the test-time compute applied to robotics. So let me start with the applied, with the application of test-time computer robotics that Sergey is advocating for, and he's advocating as a scientist, but also as of course as a business person that is a founder of a company, Physical Intelligence, that is trying to implement this in the real world. So test-time compute is a concept that we know from large language models, and it applies the idea that a model with a given weight structure can yield better results if you spend time thinking about the outcome. So instead of spitting out an answer every time you have an input, you think about it. And I think, let's say for us, Tesla customers, we can probably understand what this means in the real world. For example, Tesla, of course, is using a sort of a zero-shot, extreme low latency response to its inputs. In other words, when the car drives, there's no time to think at all. You have to immediately make decisions, and it's pixels in, actuators out. But there are situations when, at least in my version, I have the version 14 Lite version as a hardware 3 owner. That version has problems sometimes, like when there's a crazy situation, a truck is parked across the street, orthogonal to the street, because it's unloading something and covering the whole street, and the only way to pass would be to maybe go over the curb or do something like that. And like there are situations where even as a human driver, you have to shift gear from sort of this automated driving. Like when you drive a car, you can, let's say, talk to other people, you can listen to a book, you can listen to music, you can even maybe not even look fully, not even pay full attention to the road and still drive, things like that. Not that you should do that, but I'm just saying there's this automated ability to drive. But then there are situations like, as you said, with the truck, or let's say when you have to squeeze between very narrow trees or something like that, where you have to use reasoning, like you have to think, okay, what should I do now? And the same thing applies to robotics, and could in principle accelerate the deployment of robotics models. Now, having said that, I think it's not new. It's not the conversation that we've been having for years now is this tension between the bitter lesson and priors. And you could argue that in a perfect world with a lot of data and a lot of compute, you can in principle see so many scenarios, infinite amount of scenarios, let's say, that everything can be immediately retrieved, and you don't need reasoning. Or in other words, the reason you need reasoning is because you haven't seen everything, but you can connect the dots. When Christoph Columbus discovered the New World, they landed in a place that they've never seen before. They were able to move around there because they could reason, right? There's a jungle, there is, thick forests and lush and humid forests and things like that. So these types of things exist in similar form in Spain or Italy, wherever they came from, but they're not the same. So you can reason of how to actually interact. And then when you see a panther or a python snake that you've never seen before, you can still reason, okay, this thing looks dangerous, I should stay away. that's the kind of thing that, okay, in principle, if you had seen everything that is there to see in a perfect world, in principle, you could not have to reason and still do the right thing. But because it is too expensive and obviously also time-wise, not just money-wise, too expensive to train for every possible scenario, reasoning could be an application here. That's, in my opinion, what Sergey is talking about. Now, let's talk about Jim Fan. I really liked his presentation. Jim is a very creative person. He's a PhD from Fei Li, so you can see the quality. Also, he's just, you know, a smart person, not just smart in a technical way, but also in a sort of emotional and emphatic way. Like he really pulls you in with a nice presentation. And the idea here is really that we have the concept of a full self-driving robotics training pipeline. And what I mean with that is that the same concept that Tesla has used to train the full self-driving kit, which is that they've used human drivers that drive their car, and they've trained their model on the driving of the humans, which gave them two important things for learning how to drive. One, it gave them a direct connection between pixels and actuators. And second, it gave them counterfactuals. What does that mean? It means that the Tesla FSD wasn't just trained on behavioral cloning, but also on counterfactuals. In the old days, they called it shadow mode. I don't know what they call it now. But the point is, it's important that you have, like in any kind of in any in any kind of learning situation, you need to have counterfactuals, because if you don't have counterfactuals, you're not learning. Like if everything's predetermined, then you're not like you have to have ideally constantly the opportunity to do this or that, and then the this or that, this process, this iteration is what we actually call learning, because because you're learning from different you're learning different trajectories to react based on the input that you have. Now, in the case of Jim Fan's example, what he's trying to say here is that first, there's several levels of robotics training in the robotics pipeline. Number one, there is the pre-training, and the pre-training is very important because you train from video data. Let's say you have video data, which is YouTube, it's teleoperation, it's egocentric cameras, whatever feed you have. It's important to note that you can actually learn, for example, depth. You can learn spatial reasoning from statistical relationships between objects. If you have enough data, you can learn those things. You don't need to have explicit annotations or anything like that. So you can learn that a tree is in front of the car and that the car is in the back of the tree and things like that. Now, the counterfactual comes in when, and by the way, this is also something that Sergey is very high on, or very interested in, and that is the world model concept. What that means is that, so once we pre-train the model, once we have a certain understanding of statistical relationships and depth and all those kinds of things, now what we can do is fine-tune the robot to learn certain skills. And those skills can be learned by running counterfactuals, which is running a world model and thinking, okay, what could I do? What's the best thing to do? And then execute against that, and then have some sort of value function, feedback or something that tells you did well or you didn't do well, and therefore also constantly fine-tune the model and make it better and better in terms of executing that task. So that's kind of roughly the way I understand it. I think both presentations were inspiring in a way that they want to attack the robotics problem in a way that data collection and counterfactual training is nascent, it's implicit. You don't explicitly have to, let's say, collect data. The data is coming from a large set, let's say from the internet, and then you just fine tune again in a setting, for example, in a robot academy. I think we've also heard similar aspects, and I've actually just asked Rock about this. So the similarity between NVIDIA and Tesla is actually pretty striking. So they're using the same approach to the robotics model with slight differences. The main difference being that NVIDIA is trying to be open source in general, versus Tesla is closed, not just in terms of the model, but also in terms, of course, the hardware. So Tesla has a fully integrated solution to robotics, versus NVIDIA is trying to be more general, but otherwise, it's a very similar approach. And I think what's encouraging is that you have a flywheel of potentiality here to train at scale and solve the problem. Now, I want to say one more thing, and that is continuous learning, which came up also by Jerry Dvorek, the founder of Core Automation. And the point of continuous learning has been discussed last year when Richard Sutton introduced his new idea of learning from experience, or a new era of experience. He published an essay together with Silver. So what does it mean, learning from experience? Like, from a big picture perspective, learning from experience means that instead of having this iterative approach of training, applying, retraining, applying, you continuously learn while you're using the model. So that is kind of how the FSD was trained, because the FSD was trained while people were using the FSD with shadow mode. So the FSD, for example, was deployed, the car was driving, and then there was still maybe another model or counterfactual model that was trying to improve itself while the FSD was used. Another way the FSD was continuously learned is by having the person drive and the FSD running in shadow mode, and then when there were differences, the FSD will learn from the differences. So I don't know what the details are about the architecture of continuous learning, but I think the concept itself has been discussed now from several aspects. We've heard it from Core Automation. Musk has spoken about it, and NVIDIA is talking about it. And I think it's a very interesting, and it's a big theme that has been going through this Agentic conference at Berkeley. Thank you.